4-2, degrees and radians. Okay, so previously in 4-1, we used measures of acute angles and triangles given degrees. So now in this section 4-2, we're going to convert degree measures of angles into radians, and then vice versa, the opposite. We're going to convert radian measures to degrees. And then in the second section, we're going to use angle measures to solve real-world problems. Why do we do this? In lesson 4-1, we work with acute angles, but as you know, angles can have any real number measurement. For example, in skateboarding, a 540 is an aerial trick, which a skateboarder and the board rotate through an angle of 540 degrees, or 1.5 complete turns in midair. And we can take that even further, you know, any multiple of 360 as we go around. If we were to jump and spin 3 times around, that would be a 1080. So we're going to work with degree measures in this section that if you think about it, end in the same place but have different degree measures. Okay? My vocabulary: vertex, initial side, terminal side, standard position, radian, coterminal angle, linear speed, angular speed, and sector. Okay, so let's get started. So, angles and their measures. So from geometry, you may recall an angle being defined as 2 non-collinear rays that share a common endpoint known as a vertex, just like we see right here. Okay, we have 2 lines or 2 rays that are not on the same line, and they share a common point called my vertex. Okay, we're also gonna talk about my initial side and my terminal side. Okay. When we talk about angles in trigonometry and going forward, we're always going to put my initial side of my angle where this angle starts on the x-axis. So this, where I start my angle, this initial side right here, is always going to be seated on the x-axis. When I do this, I say that my angle is in standard position. And if I measure as I measure my angle, all right, this would be the measure of my angle right there, however big that is. Looks like it's about 100 degrees. Okay. So when I measure my angles from standard position, I always start with my initial side on the x-axis. Okay. Now, the measure of an angle describes the amount and direction of rotation necessary to move from the initial side to the terminal side. Should make sense. When we talk about positive angles, okay, we are going to move in a counterclockwise rotation. Okay, so that means we're going to start at the x-axis and we're going to go left. Okay, we're going to go counterclockwise, the opposite direction of a clock, this way. Okay, that's not the way a clock goes. That's the opposite direction of a clock. Okay, when we talk about negative angles we measure in a clockwise direction, like that. Okay, so I could measure this angle from my initial, my initial side to the terminal side. I could measure it like this, but then it would be a positive angle. If I wanted to measure the negative angle, I would have to go the other way. I would have to go in a clockwise direction. Okay. So most of the time, when we're talking about trying to measure an angle, we're going to use the most common angular unit called degrees. Everybody should know what degrees are. Okay? This is equivalent to 1/360th of a full rotation. If we go counterclockwise, of course, because we want to measure a positive rotation. So you can see from the circle right here that as I go around the circle, okay, I go through all the degrees from 0 to 360. Okay? And when I go all the way around, that would be one complete rotation, which is 360 degrees. 180 degrees is half a rotation. 90 degrees is a quarter of a rotation. And if you think back to the 2 biggest and most famous triangles that we talk about in geometry, which are a 30, 60, 90 triangle and a 45, 45, 90 triangle, you'll see that this circle right here includes a 30, a 60, and a 90, and a 45, and a 90 again. So those angles are going to become really important to us, especially as we move forward with trigonometry. But another thing to realize is that all of these things are marked as we go along the circumference of the circle, as we go around the circle. Okay. Now, degrees. If we want to measure an angle, degrees are great, but sometimes we want to be a little bit more accurate. It's tough to tell if there's an angle right here, right next to, well, like right next to that. Maybe it's 41 degrees, maybe it's 40, or maybe it's 44 degrees, maybe it's 43 degrees, maybe it's somewhere in between there. So we do have a way to become more accurate with degrees. We use something called degrees, minutes, and seconds. So we can subdivide degrees into 60 minutes and subdivide each minute into 60 seconds. It should be familiar if you think about time, obviously. Okay? And this comes from ancient Babylonians who used a base 60 number system rather than a base 10. So let's see how to convert between degrees, minutes, and seconds and decimals. So write each decimal degree measure in DMS form and each DMS measure in decimal degree. Okay, and we're going to round to the nearest thousandth. So what we're going to do with this one, okay, we're going to change this degrees into degrees, minutes, and seconds. Okay, so we are going to start with 56 degrees because we have 56 degrees right there. Okay, so now we have to turn this decimal into minutes and seconds. Well, I could use a straight conversion factor and realize that this is what I have left over, 0.735, and I can multiply it by 60 seconds in 1 degree, and these are degrees. So my degrees would cancel out, and now whatever this calculation gives me would give me the number of seconds. And when I work it out, it becomes 0.735 times 60 gives me 44.1. Okay, so that means I'm going to have 44 minutes. Now I'm going to do it again, but I'm only going to use the decimal part. Okay? So I'm going to take 0.1, I'm going to multiply it again by 60, and these are 0.1 minutes. So now I can say that there's 60 seconds in 1 minute. And I'm going to use that conversion factor right there to give me the number of seconds. And multiplying these two together gives me a 6. So this answer would be 56 degrees, 44 minutes, 6 seconds. Now, we don't usually go any further than that. If there was a decimal to this, I would just put it as 6.5 seconds. Okay? We don't usually go any further. We don't break down seconds into any other measure. Okay? Let's try the other way. Let's start with degrees, minutes, and seconds and get a decimal. Okay? So now we're going to take 32, because it's going to be 32 point something because we're starting with 32 degrees. Okay? And we're going to add this fraction. Well, I want to turn those number of minutes, I want to turn 5 minutes into degrees. Well, I could take 5 minutes times, well, in 1 degree, there's 60 minutes. So I'm going to take 5 divided by 60. And then I'm going to try to calculate the number of seconds in a degree. Now, don't do this. This is not 28 times 1 over 60 again, because this is 28 minutes, and I want to change it to degrees. If I did this calculation right here, 1 over 60, I would be changing it into minutes, 28 seconds, sorry. This is 28 seconds. I don't want to change it into minutes. I want to change it into degrees. So therefore, I need to write how many seconds are in 1 degree. Well, 60 seconds in a minute, 60 minutes in a degree. That gives me 3,600 seconds in 1 degree. So now, when I calculate this, I have 32 plus 5 divided by 60 plus 28 divided by 3,600. and I get 32.09. So it's 32.09 degrees. Okay? Now, most calculators have a way to convert degree values to degrees, minute, and seconds. Somewhere there's a DMS button. Sometimes it's under the angle menu. Sometimes it's on a second function. Sometimes it's a button that looks like this: degrees, minutes, seconds. Some sort of button that looks like that. It's tough to tell. You're really going to have to look into your calculator and figure it out. Some calculators are better than others. This calculator is not great, but I still can use it, and I can still plug in 213.875, press degrees, minutes, and seconds, which is, oh, whoops, try to circle that. Okay, so let's clear that. 213.875, press degrees, minutes, and seconds. And the problem with this calculator is it's tough to tell what that answer is. But it's 213 degrees, 52 minutes, and 30 seconds. Hopefully your calculator can do it a little bit better than this one, and it's just up to you to figure out how it works. Okay. So, measuring angles in degrees is great, and it's appropriate when applying trig to solve real-world problems, such like surveying and navigation, which is where they use degrees, minutes, and seconds. It's in navigation. Okay? But for other applications with trig functions, using angles measured in degrees gives us a big problem. Okay? Degrees have no relationships to any linear measure. Inch degrees has no meaning, right? That's not something that actually exists. So to combat this problem, we use something called radians. Okay? And radians is something that you're going to have to get used to. It's a different way to measure an angle, and it's the most common one, and it's the one that we're going to be using for most of the rest of this chapter and next chapter. Okay? So you have to get used to radians. Okay. So what is a radian? Okay. The measure theta in radians of a central angle of a circle is equal to the ratio of the length of the intercepted arc S to the radius of the circle. So that's all a radian is, and that's my formula. That theta is equal to S over R. So that is the length of this divided by the radius of the circle. Okay. Now, a central angle has a measure of 1 radian if it intercepts the arc with the same length as the radius of the circle. Okay, so where the radius and the arc are exactly the same length, that's when a radian equals 1. And it happens at about 57 degrees, which might seem weird, but if you think about it, if we think about the distance, I just drew right there. Let's do that in another color. Let's do that in red. The distance all the way around the circle is going to be the circumference, which is equal to 2 pi. Okay? So if I go all the way around the circle and I divide out the radius, okay? So my full rotation around the circle is going to be 2 pi. Okay? And then when I divide out the radius to get the number of radians, you're going to see that radians have everything to do with pi. Okay? So as long as the arc length S and R are measured in the same linear units, so as long as we're talking about inches or centimeters or meters or whatever you want, that if S is meters and R is meters or centimeters or whatever, that the two units are going to cancel out. Okay? Therefore, radians, when we actually calculate it, is unitless. Okay? Therefore, the word radian, or its abbreviation, rad, you'll see sometimes, is usually omitted when writing the radian measure of an angle. We don't write it. We just write how it is related to pi. Okay? And let's look a little bit more into that. Okay? So the central angle represents 1 full rotation counterclockwise, about a vertex, corresponds to the arc length equivalent to the circumference of a circle, which is 2 pi r. Okay? So from this, you could obtain that 1 rotation is going to be 2 pi r divided by r. R's cancel out. So we have 2 pi radians. So 1 radian, one circuit all the way around the circle is going to be 2 pi radians. Okay? Halfway around the circle is going to be pi. Okay? Because that's half a rotation. So that's 1/2 times 2 pi, right? Pi. Okay? A quarter of a rotation around the circle is going to be pi over 2. And then a third of the way around this, or sorry, a sixth of the way around the circle is going to be pi over 3. Okay? And these are going to be, these distances become more and more common to you as we go through trigonometry. Okay? Interesting note here is that 1 degree is equal to 0.017 radians, and 1 radians, like I said before, is equal to 57.296 degrees. So it's not really useful to try to think about circles in terms of, well, I have some measure of pi radians. Let me turn that back into degrees. Like, it might not work out perfectly. Okay? And especially if you evaluate pi as 3.14, it's very tough to tell where those angles are. So most of the time when we're talking about radians, we're going to leave them in terms of pi. Okay? So because 2 pi radians and 360 both correspond to 1 complete revolution, we can write that 360 is equal to 2 pi radians, or 180 is equal to pi radians. Okay? And this relationship will be used to give us a couple of equivalent statements, that 1 degree is equal to pi over 180 radians, and 1 radian is equal to 180 over pi degrees. Okay? Now, this is important as well. If there's no units, we're talking about radians. If degrees are intended, you have to use the degree symbol. Okay? So if you don't put any units, you have to assume that that is radians. Okay? So from these two conversions right here, we can get my 2 formulas to give me radians. Okay? Here they are. To convert a degree measure to radians, multiply by pi radians over 180. To change radians to degrees, multiply by 180 over pi. Okay? The way I like to remember this is if I want something in radians, it means I'm going to want pi in it. That means pi is on the top. And if I want something in degrees, I'm going to start with something with pi, which means I want to cancel it out. That's why it's on the bottom. Okay? And working with these is fairly straightforward. All right? So let's try. Okay? Let's change these. Write each degree measure in radians as a multiple of pi, which is usually how we want to leave it, and each radian measure in degrees. So for 120 degrees, I'm just going to multiply this by pi over 180 degrees. Okay? Now, you can multiply these together, but you're going to have to simplify it eventually. And when we simplify this, we get 120 over 180. We can just simplify it like that, and we get 2 pi over 3. Okay? You don't have to write any symbols or anything else to tell you that it's a radian, right? You just assume that it's a radian because there are no units. Okay? With negative 45 degrees, same thing. It's okay that this is negative. All a negative angle means is that we're going this way. So negative 45 degrees is something like that. Okay? So change this into radians. We get pi over 180 degrees. The degrees cancel out, and we're left with a unitless measure, which is still going to be negative, and now we would get negative pi over 4. Okay? Which is still that angle right there. Okay? We're still going the same way. We're still going the same distance. Okay? And we're still going negative. Okay? 5 pi over 6. Now I want to change this to degrees. So to change it to degrees, my conversion factor is opposite. So 180 degrees over pi. And notice that pi is going to cancel out. And we can simplify this, which gives me 150 degrees. Same thing here. My answer is going to be negative. Okay, so we're going to multiply by 180 degrees over pi. And my answer is going to be 3 times 180. It's going to be a negative 270 degrees. Okay? So, degrees and radians. Very important to remember how to change them back and forth. But even more important is to get more comfortable thinking of angles in terms of radians, okay? And not have to actually convert to degrees all the time. Just to be able to get more and more comfortable and to understand where these types of angles are, especially the big ones. Things like pi over 2, 3 pi over 2, pi over 4, pi over 6, like anything having to do with 2s, 4s, and 6s, those are going to be and 3s. Those are going to be the angles that we really care about the most. Okay? So, next, we're going to talk about something called coterminal angles. Okay? By defining angles in terms of their rotation about a vertex, two angles can have the same initial position and terminal sides, but different measures. These angles are called coterminal angles. They end in the same spot. In the figures below, angles alpha and beta are coterminal. Okay? The first one is an example of having a positive and negative coterminal angle. So if we look at alpha there, it looks like, well, halfway around the circle is 180, and it looks like it goes about halfway in the next quadrant. So that's going to be 180 and about 45. Okay, so that means this angle right here is going to be 225. Okay, now if I were to measure it the other way, realizing, of course, that since I'm going clockwise, beta is going to be negative, and so that one looks like it's going to be about negative 135. Okay. Also, you got to be able to think about this in terms of pi. So the red one would be about 5 pi over 4, and my blue angle would be a negative 3 pi over 4. Okay? And hopefully you'll get more comfortable with those type of angles. Okay? And if you can't think of those right off the top of your head, use a conversion factor for now. Okay? This is going to be a positive and negative coterminal angle. Now, this picture on the right shows us two positive coterminal angles. Alpha, which looks to be about 60 degrees, okay? And then beta, which still starts at the same spot, but now goes all the way around once, and then another 60 degrees. So that would be 360 plus 60 would give me 420 degrees. Okay? And of course, if we think about that in terms of pi, this would be pi over 3, and the blue one would be, that would be 2, that would be 7 pi over 3. Okay? A little bit more than 1, because once around is 2 pi. Okay? So those are all coterminal angles. And of course, in trig, angles are used usually with Greek letters, right? We used theta a lot in the past. So now, to help show you other angles, we got alpha and beta. Okay? So let's draw some coterminal. Oh, wait. So two positive coterminal angles are shown, differ by 1 full rotation. A given angle has infinitely many coterminal angles found by adding or subtracting integer multiples of 360, or 2 pi radians. Okay? So all that means is that I can go around this circle as many times as I want and keep getting another coterminal angle with my first angle. Okay? So if I want to find coterminal angles, I take my initial angle and add 360 times a number, any number, right? 1 rotation, 2 rotations, 3 rotations, however many rotations I want. Or if I want radians, alpha plus 2n pi, right? because 360 and 2 pi are once around circle if you're measuring in degrees or radians. So if I want to find some coterminal angles here, okay, what I would do is I would first draw 45-degree angle. It's about right there. Here's my initial angle, 45 degrees. So if I want a positive coterminal angle, right? So draw one positive and one negative coterminal angle. So if I want a positive coterminal angle, I would have to go all the way around and then another 45 degrees, which would give me 405. Okay. Now, if I want a negative coterminal angle, I would go this way, clockwise, which would give me an angle of negative 315. Okay. So the same thing, only with radians, okay, negative pi over 3 is going to be right about there because it's negative 60 degrees. So this is going to be negative pi over 3. So a positive coterminal angle would go this way. And my positive coterminal angle would be 5 pi over 3, which I can get by taking 2 pi and subtracting pi over 3. And my negative coterminal angle, well, now to get a negative 1, I have to go, let's go outside. I have to go all the way around and then a little bit more. So all the way around, this can be 2 pi plus another pi over 3, which is going to be 7 pi over 3. And those are my two, my positive and negative coterminal angle. Coterminal, end in the same spot. Okay, so now let's take all this stuff and let's start using it. Let's start using it with some real world applications. Okay, so first, solving theta equals S over R for arc length S yields a convenient formula for finding the length of an arc, right? All we have to do is just multiply both sides by R and we get that formula right there. That if theta is a central angle in the circle of radius R, the length of the intercepted arc is given by S is equal to R theta. Very important. Theta is measured in radians. Always, 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 always in radians. Okay? If it's not in radians, put it in radians. If you wanted to, you can use this little formula right down here to help you put it in radians, but I usually just like to change it into radians first. So just take pi over 180 and change the angle to radians. Okay? And this will find the length of an arc. So let's find the length of an arc. Okay? So find the length of the intercepted arc in each circle with the given central angle, measure, and radius, round to the nearest tenth. So we have pi over 4 and 5 centimeter radius. Okay, so the length is given in radians, which is perfect. And all we're going to do is use my formula that S is equal to R theta. So that's going to be equal to 5 times my angle, pi over 4. 5 times pi over 4 is 5 pi over 4. Now, when we're talking about a circle like this, it's okay to just leave it in terms of pi. Okay, but if we had a situation where we actually want to see how big this is, we could actually work this out. Okay? When we work it out, we get that it's about 3.9. Right? Just 5 times 3.14 divided by 4. Okay? So, and of course, the unit. What unit is this? Well, 5 is centimeters, and radians is unitless. So this is centimeters. Okay? And that's what this says right here. That R is equal to 5 centimeters and theta is pi over 4 radians. So this is 5 centimeter. The answer is 5 centimeters, not centimeter radians. Okay, radians is a unitless measure. Okay? And of course, when we're talking about real world problems, probably best to calculate this out. Okay, because I don't really know how long 5 pi over 4 is. So best to work it out. Depends on the problem. Let's try another one. 60 degrees. You cannot calculate arc length with a degree measure. You must first change it into radians. Pi over 3. Okay? And hopefully you get more used to pi over 3 as a radians. Now we can use my formula. S is equal to r theta. So my arc length is going to be my radius, 2, times my angle. And so my answer is going to be 2 pi over 3 inches. And I'm going to change that into a decimal again to give me 2.1 inches. Okay? Next. So we can use the formula for arc length to analyze circular motion. So the rate at which an object moves along a circular path is called its linear speed. If you think about the outside of a tire as it spins around. That's a linear speed. The rate at which the object rotates around a fixed point is called the angular speed. Okay, so that's something spinning around. Linear speed is measured in units like miles per hour, while angular speed is revolutions per minute. How many times it's spinning around? Linear speed is how sort of fast it's going. There's two formulas for this, linear and angular speed. Okay? So suppose an object moves at a constant speed along a circular path of radius r. If s is the arc length traveled by the object during time t, then the object's linear speed, v, is given by that formula right there. V is equal to s over t. S being the arc length, t being the time. And if theta is the angle of rotation in radians, so through which the object moves during time t, then angular speed omega, not w, omega, is given by omega equals theta over t. Okay? And we can even throw in, we can simplify, we can change this formula if we have to, that s is equal to r theta, and if we need it, we can change s to r theta over t. Okay? So depending what information that we have, we can use what we need. Okay? So let's look at a bicycle. Okay? A bicycle messenger rides the bicycle as shown. So we have our bike right there. It's got a 30-inch wheel. During one delivery, the tires rotate at an angle, at 140 revolutions per minute. Find the angular speed of the tire in radians per minute. Okay, so because each rotation measures 2 pi, 140 revolutions corresponds to an angle of rotation of 140 times 2 pi. Okay, so this thing is spinning around, right? 140 revolutions per minute. We want speed in radians per minute. Okay, it's spinning around 140 times. If we multiply that by 2 pi, we get 280 pi. Okay, so now we can use my formula that omega is equal to theta over time. And now we have that this went 280 pi in 1 minute. Okay. So if I were to calculate this, working, of course, leaving it like this does not really make a lot of sense. So I'm just going to have to multiply this out. So that's going to be 280 times 3.14, which gives me 879.2, and this is a unit of radians per minute, which is what I wanted. If this was not the unit that I wanted, then I would have to take my answer and convert it. Okay? Like the next problem. Okay? But for now, right, angular speed we can find just with my formula for omega. Okay? Let's try one where we have to do some conversions. On part of the trip to the next delivery, the tire turns at a constant rate of 2.5 revolutions per second. Find the linear speed in miles per hour. Already I can tell that this problem is going to be a pain. The units don't match. Okay, we want revolutions per second, and we need miles per hour. I get my picture. Okay, so here's my bike. Okay, my bike, I know first that a rotation of 2.5 revolutions corresponds to something in radians. So if I want to take this 2.5 revolutions, let me convert that to radians. Well, that's going to be 2 pi times 2.5, which gives me 5 pi. Okay, so that's my theta. Okay, so what do I know? I know theta. I know time, right? Because this is revolutions per second. Okay, well, I don't know S. I don't know my arc length, but I can figure it out because I do know the diameter. Arc length, the formula for arc length isn't diameter. I need my radius, but if I know my diameter is 30, my radius is going to be 15 inches, of course. Okay, so now I have all the information that I need, and if we go back to my formula, ooh, there it is. Okay, we know that V is equal to R theta over T. Okay, so quick calculation. So we have now that V is equal to R theta over, okay, 5 pi is unitless, R is inches. Okay, in this case, we are going to really have to keep track of my units. Okay, if I want to do this now, I can, and this would give me 75 pi inches per second. Okay, that's not the answer that I want. I want miles per hour. Okay, let's worry about time first. 1 second on top, so I can cancel it out. Okay, let's go to 60 minutes. Now, I could have went right to hours if I wanted to, which would have been okay. So 1 minute oh, sorry. Bad calculation. 60 seconds in 1 minute times 60 minutes in 1 hour. Okay, so now we got hours. Okay, now we just have to go from inches to miles. So in 1 foot, there is 12 inches. And now I put inches at the bottom, so again, they can cancel and I'm left with feet. Now, you should know this, but you might not know it exactly. But in 1 mile, there are 5,280 feet. Okay? So when I multiply these all together, let's do it. So we got 75 times 3.14, 75 pi times 60 times 60 divided by 12 divided by 5,280, which gives me 13.4 miles per hour. Okay. So to recap, revolutions, change that to a radian measure. Okay, if it was degrees, change it to a radian measure. Okay, that'll give me theta. Time the problem told me. Radius the picture told me. Okay. Get my answer. Convert my answer. Okay. Last one. Okay. So now, if you recall from geometry that a sector is a part of a circle, it's a region bounded by a central angle and its intercepted arc. Okay. So a sector is something like that shaded part right there. Okay. Of theta. Right? It's just a piece of a circle. Okay. The ratio of the area of a sector to the whole circle is equal to the ratio of the corresponding arc length to the circumference of a circle. So if we have these formulas right here, we know that the area of a circle is proportional. The ratio of that is going to be equal to the arc length and the circumference. So we have the area of the sector, the area of the circle, the arc length of whatever it is, in this case QRS, divided by the circumference. Okay. So when we work all this out, we're left with a nice formula for sector area. Okay. So if we want to know the area of a sector with a radius r and a central angle theta, it's 1/2 r squared theta, where theta is measured in radians. Again, very, very, very important. Theta is measured in radians. Okay, we'll even highlight it. Okay, theta is measured in radians. Very, very, very important. Okay, so let's find the area of this sector. So to find the area of this sector, right, we got a nice easy circle here. We know my r, we know my theta, everything's all set up. So my area is going to be 1/2 r squared theta. So my area is going to be 1/2 3 squared. Theta is 7 pi over 8. Okay. Multiply these all together, we would get 63 pi over 16. Okay. Really not a very useful convention right there. So we're going to change that to an actual number. We're going to multiply that out and get 12.4. 12.4 what? Radians is unitless, so this is going to be centimeters. Okay. Let's finish with a problem that's a little bit harder. Okay. Windshield wipers. Okay. So, find the approximate area swept by the wiper blade shown if the total length of the windshield wiper mechanism is 26 inches. So that means that this thing right here, the whole mechanism is 26 inches. Let's not do that. Inches. Okay? And, of course, this piece is 16 inches. Okay? So, well, because it's not a whole sector, that would be the whole sector. I can figure that out. Okay? We're going to find the area of the first piece, and then we're going to find the area of the second piece. Okay? So the area swept by the wiper blade is the difference between the areas of sectors with if we thought about this sector right here, and then the whole sector right there, if I found the area of the big one, and then subtracted out this little sector right there, that would give me the area of the windshield wiper. Okay. See it? All right, and we know that this radius from here to here is 10, because the whole wiper is 26. Okay, so now first of all, degrees, very bad. So let's first change 130 degrees into let's multiply this and get a 13 pi over 18. Not a very nice number, but that's okay. Okay. So next, I know that my area is going to be equal the area of the big guy minus the area of the small guy. All right. So the area of the big guy is going to be 1/2 26 squared times 13 pi over 18. And then we're going to subtract off 1/2 10 squared times 13 pi over 18. Okay? If I work both of these out, I should get 2197 pi over 9 minus 325 pi over 9 as well. Okay? And then calculate this out. We get to be about, we get to be 208 pi, which is going to be equal to 635 point, 653.5. And it's going to be area, so that's going to be inches squared, because both of these are inches squared. Did I put a units up here? No, I didn't. It should be centimeters squared. Okay? I cleared that off, sorry, but my units up there, I think I put centimeters, should have been centimeters squared, area. Okay? And that was 4-2 degrees and radians.